cards for blackjack. But yeah, anyways, we're starting to record now. So chapter 3, let's take a look at these notes. Basic concepts of probability and counting. Before you actually get into more advanced stuff like that and probability, we have to start off with the basics, which is basically learning how to count all the possibilities of something coming out. You guys remember yesterday when we did the Desmos activity where you had a spinner and you had to see where it lands on red or blue, right? You guys were able to count how many outcomes there were possible, right? It was either red or blue. So there was 2 possible outcomes. And then there was a question that asked, well, how could you make it so those become less likely? And a lot of you guys are saying, add a third color. And you add a third color, whether it be green or black or whatever color you picked. And that would cause you to change the other probabilities because now you're counting more possible outcomes. And that's what this chapter is going to be about, right? Talking about the probability when you look and see what possible outcomes there are to have in these problems, okay? So if you joined in a little bit late, the notes, I'll post the link for the notes right in here again for you. And you can go ahead and make a copy of it on Google Docs if you don't like Cami. And if you're okay with Cami, you can go ahead and do it on Cami as well. Good morning, Demaya. Welcome, welcome. I put the link into the chat so you can follow along with those notes. There is a lot of vocabulary in this first section, but I don't want you to stress out over it. It's just what they're called, right? And when you actually go in there and start doing what it is, you'll be like, oh, this is actually really easy to understand. So let's take a look here. We got probability, experiment, outcome, sample space, event, simple event, fundamental counting principle. Man, you gotta be careful whenever you see things that say the word fundamental, right? We'll talk about that when we get there. Classical probability, empirical probability, law of large numbers, range of probability rule, and the complement of an event. Whew. So much, so much. So let's start off here. This is where your notes come into play. Google Docs is superior. I mean, if that's what floats your boat, Marissa. If you like it on Google Docs, you can go with Google Docs. That's why I gave you the link for it. So you have both possible outcomes. You know what I should do? I should give it to you guys as a Google Doc. And if you like Cami, you can open up Cami. You don't have to use my links on Cami. You know, I just realized this. You can open up Cami yourself because it's included with your school email account. So you could open up Cami and then open up the doc in the Cami. And then when you finish, download that doc as a PDF and then upload. That's just too much work, isn't it? This way you could just hit the submit button and it's already done for you. Man, I'm in a conundrum of how to make it so you could turn it in either way. Oh, well, we'll figure this out. All right, anyways, let's move on. The probability experiment, an action or trial through which specific results, counts, measurements, or responses are obtained. So you can make something a probability experiment, right? Almost anything. As long as you're looking to record the action, the trial, or a specific result of that thing. So for example, if you take a coin, which I do not have. Do I have a coin? I do have a coin, right? You can make this man, I'm so boring. I turned off the lights in my class. Come on, turn back on. There you go. So you can, for example, make a trial where you record how many heads you get and how many tails you get from flipping a coin, right? You're just counting that, right? Or you're seeing that. You can also do a probability based off of responses. You can calculate the probability that people say they love Mr. Nakmi's class by going and asking them, hey, what is your opinion of Mr. Nakmi's class? And you can record down, do they love my class? Do they hate my class, right? And that's a probability experiment. Once you have the numbers recorded, you can say, 10 people said they love my class and the other 10 people don't know who Mr. Nakmi is. So then you can say, it's a 50-50 chance that you'll ask somebody and they'll say that they love my class. They'll never say that they hate my class because that's impossible, right? It'd be like probability of that happening is 0, right? Everyone loves my class, right? All right. Oh, wait. I learned this one, right? You guys told me about it. That's a no cap, right? It's a no cap. All right. Outcome. The results of a single trial in a probability experiment, right? The result of a single trial in a probability experiment. So the outcome is not all the possible outcomes. It's just what the outcome is for that one time that you do it. So for example, I flip this coin right here, call it, comes out heads. The outcome is heads. That's all it is. It's not the outcome is heads or tails, right? I mean, it could be heads or tails, but we're looking at a specific single trial and seeing what we get. Tails. How good are you guys? Do you guys think you can call it? All right, call it real quick. What do you guys think? Heads or tails? Just for the heck of it. You guys, who wants to type it out? You guys going with tails?
Tails.
Oh, some more people tails. Some people typing out heads. Let's take a look. It is heads. It's heads. Rigged. I don't know. So that's the outcome, right? The one thing that you measure. Now, this is the part where things get interesting. The sample space. I know you're like, these terms, but the sample space is what will help you to figure out what can you even make a call on for the outcome. The sample space is the set of all possible outcomes of a probability experiment. So the sample space for a coin, right? You guys knew it's either going to be heads or tails, right? Because that's all a two-sided coin is. But that wouldn't work if you were, let's say, rolling a die, right? The sample space for a die is not just heads or tails because a die doesn't have heads or tails on it. Not only that, it has a larger sample space, right? The sample space for a six-sided die. Do I have a die here? I don't. Do I have a die there? No, I don't. No. Where are my dice? They're not here. Anyways, so on a die, for example, the sample space for that one is not heads or tails, but instead would just be the numbers 1, 2, 3, 4, 5, 6, right? Those are the dots that are on a die, right? And that's the idea behind a sample space, is just listing out all the possibilities that you could get. And that's a big thing in probability, right? If you are ever looking at something and you're trying to figure out like what's the chances of this happening or that happening, you need to measure and see what are all the possibilities that could happen, right, in that sample space before you actually do it. So that's what a sample space is. The last one is called an event. An event consists of one or more outcomes and is a subset of a sample space, meaning you care about a specific outcome in a sample space. So for example, when you're flipping the coin and you guys are like calling out heads, right? Heads would be the event out of the sample space of heads or tails, right? So when you're talking about an event, you're talking about a specific outcome that you want or that you care about or what it is that you're recording. For example, if you're looking at a sample space, right, and you're rolling a die, the sample space for rolling a die is 1 through 6. An event could be looking at only answers where the die comes out as even. Excuse me, what the heck? Maybe I should drink some water. There we go. Okay, so yeah. So an event could be like, oh, I only care about it when the die is even. Much better, much better. All right, and the outcome was, let's say they rolled the die and it came up 3. Okay. Do you guys see the difference between an event and a sample space? Sample space is all possibilities. An event could possibly be all of them, but it could just be a subset of it, which is just pieces of it, right? It could just be like, oh, just the evens or just the odds or numbers 1, 2, and 3, and someone else would be 4, 5, and 6. Right? An event could just be 3 itself. It could just be 5 itself. In fact, if you ever get old enough and Vegas ever reopens and you guys decide to go gamble, an event could be what it is that you're betting on. Right? Like if you're betting, hey, that die is going to come up 3, that's the event you care about. Michael, you're a little bit confused? Yeah, I guess it's a little weird to talk about it that way, but think of it this way. Think of an event as a set rule of a specific outcome that you care about. So like earlier, right, when you called heads when I was flipping this coin, right? That was an event. The event is that you're thinking that the coin is going to land heads. That's all it is. But your event could also be more than just one thing. It could be multiple things if you want that event to happen. Like, for example, rolling a die, instead of saying, I'm going to bet that it's going to come out 3, you could make the event say that, oh, it's going to come out odd, right? My event is that the die is going to roll out odd. That's another possible event. You could also say the event could be even, or it could be higher than 3 or lower than 3. Those are all different possible events. They're different possible combinations. of the sample space. That's all an event is. It's just looking at different combinations of your sample space. Does that make sense? Does that make it a little bit clearer, hopefully? Right? The outcome is just what happens when you do the experiment. The event is a subset of like things that you care or things that you want to happen, like things that you're trying to bet on pretty much. Okay. So you're like, you want to make a bet with your friend and say, hey, I bet you this die is going to come up even. So that means that the event that you care about is 2, 4, and 6. That means your friend would care about the event that the die comes out odd, which is 1, 3, and 5. All of which are part of your sample space. All of which are part of your sample space. All right. Hopefully that made sense. And if not, don't worry about it. You'll pick it up as you go. The more you look at this stuff, the more it makes sense as you go through it. I'm not lying. Yeah. That's yeah. It should work out that way. All right. So let's take a look here. Let's say we have a probability experiment where you are tossing a coin and then rolling a 6-sided die. Describe the sample space. So first things first, right? This probability experiment consists of 2 parts. This person has to flip a coin and get a result from tossing that coin. And then after that, they need to roll a 6-sided die. How many possible outcomes are there when you're tossing a coin? What are those possible outcomes? Calvin, come on. You know, Lewis, that's right. There's 2 possible outcomes. You're either going to get heads or you're going to get tails, right? Heads and tails, right? I'm going to list that out. That's the sample space, right? That's the sample space for tossing a coin. Calvin, I'm curious now. What do you think that third one is if you're going to go with 3? What do you think it is? All right. While Calvin's typing that out, vertically suspended. Can you do that? Can you flip a coin to get it to land vertically? Demise agreeing with that. Don't encourage that. Probably not. Yeah, I've never actually seen it, but it's not impossible. I've seen it on TV. We'll talk about it, but yeah. All right. Now, what's the sample space for rolling a 6-sided die? I hope you guys will see that rolling a 6-sided die has 6 possible outcomes. When you roll it, it could either come out 1, 2, 3, 4, 5, and 6. Okay? So what's the sample space for this event in total? This event where you're tossing a coin and you are rolling a die. Well, what are the possible outcomes is basically what's being asked. Are you ready for this? One possible outcome is that you flip the coin and you get heads, and you roll the die and you get a 1. A second possible outcome is that you flip the coin, you get heads, and you get the outcome on the die as a 2. You ready? You see what I'm trying to do here? What's the next possible outcome? You flip a coin, you get heads, and you roll the die and you get 3. That's another possibility. Yeah, you're already catching on. It will be H3, H4, H5, and H6. That's one possible combination for getting heads, right? You flip the coin, you get heads, and then you're going to roll the die. You're going to get either 1, 2, 3, 4, 5, or 6. But that's not the sample space. That's only half of the sample space. You know what the other half of the sample space is? You can still roll a 1, but instead of getting heads there, you can also get tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, and tails and a 6. This right here represents your sample space. Demaya's got it right there. That's perfect, Demaya. T1, T2, T3, T4, T5, T6. Right? This is your sample space. That's your sample space described. By the way, how many possible outcomes are there? Can you guys tell me? Count that out. What is that? How many possible outcomes are there for the sample space? How many elements are in here? How many elements? There are 12 total elements. That's right. 12 total possible outcomes in this sample space. Yeah, that's pretty much it. That's how you count this out. You can kind of see like, oh, there's this one, this one, this one, this one, which is kind of neat. I think it's kind of cool to see. And if you actually were to roll a die and flip a coin, it has to be one of these 12 that you have listed. There's no other possibilities unless you really want to take into account that it lands vertically. But if that's the case, I don't know who would win that bet. Is that just one where like do over and everyone's just in like awe of that coin landing on its edge? You know what? We can actually Google this. 14 multiplier. And you flip a coin and have it land on its side. It rotates edge over edge. It is possible for a coin to land on its side. By lining up. I'm supposed to say on its edge. On its edge. However, even on a flat surface, it is possible for a coin to land on its edge. That's the one I was asking. I don't know why I said side. Coin flip lands on edge. Nickel flip. All right. This has nothing to do with our probability, but I just want to watch this video. I'm going to turn on the volume. That doesn't count. He's tossing flipping it though. Does that count? Huh. He's so stoked that it's landed. Imagine doing this for hours. What is that surface that he's flipping that on? All right. Anyways, knock me anyways. I mean, he's still flipping the coin, so it counts. I guess. I'm not going to put that in my sample size, so. So he got no. That's mean, Brenda. That's mean. He's competent, Not competent. He's passionate. That's the word I was looking for. He's passionate about it. That's all. All right. Let's take a look here. Let's do this one together before we move on. Okay. For each probability experiment, determine the number of outcomes and identify the sample space. Not in a mean way. I mean, leave it at that. All right. A probability experiment consists of recording the responses to a survey statement at the left and the gender of the respondent. So here are the responses on this survey. They either agree, disagree, or have no opinion, right? So that's the first part. They're either going to agree, disagree, or have no opinion, and the gender of the respondent. To show you how outdated this is and just to keep it simple for today, we're going to say that for simplicity's sake, we're only going to look at male or female. I know there's a whole discussion about a lot of other things, but just to keep it simple for our sake and just for easy to count, we're going to say it's either male or female, just to make it easier for us today. I know that there's a whole discussion about all that stuff, but we'll leave that for your other classes, all right? So just for math's sake, just to make it easier, let's say I was recording here and we see that one person agrees, right? So if we're looking at the sample space here, right? One thing we can say is that they agree. That's the first thing we measure. And then what else do they have to measure? After they agree, we also measure to see if they're male or female. So they could agree and they could be male. They could agree and they could be female, right? What else could happen? What if they don't pick agree? What's the other options they could pick? They could disagree and they could be male. They could be disagreeing. Knock me, you can spell. Disagree. And they could be female. They could have no opinion. They could be male. And they could have no opinion. and they could be female. How many possible outcomes are there for this sample space? What do you guys count? Agree male, disagree male, no opinion male. Agree female, disagree female, no opinion female. I say this is the sample space, and there's a total of 6 in this one. That's the part that makes it tricky, right, Lewis? Is it 3 or is it 6? And you're right, there are 3 possible responses. But since we're also recording the gender, I have to see if they agree and they're male or if they agree and they're female. That makes 2 for each of those options. So that makes it out to a total of 6. Makes it out to a total of 6. All right. All right. Let's go ahead and see if you guys can try this next one. The probability experiment for this you try is the same as the survey that they have above. They're either going to agree, disagree, or have no opinion. And they're also going to record their gender. But I want you to also add in, what if they're also taking into account their political party? And in this case, now I know there's a lot more political parties, but just to keep it simple, let's say the political parties they have here is going to be either Democrat, Republican, or other. So those are the 6 options we did earlier for agree male, agree female, disagree male, disagree female, no opinion male, no opinion female. But can you guys do that and add on these features as well? Can you see how many possible outcomes we're going to have if we add on that they're Democrat or they're Republican or other? Can you guys do that real quick? I don't have a pair deck for this one. Can you guys just do this in your notes and see how many, what is your sample size going to be for this you try right here? I already did this part. I already did the agree and male, right? So the next one you could be is going to be, you ready for it? It's going to be agree. You don't have to write out the whole word, by the way. I'm just going to write A. They agree, they're male, and they're a Democrat. That's one. The other one, the possibility is that they agree, they're male, and they're Republican. And the other one's going to be they agree, they're male, and they're other. So can you guys do that and type into the chat for me? What do you guys think the total count is going to be for this sample space where they agree, disagree, no opinion, they're either male or they're female? And the last one is if they're a Democrat, Republican, or other. Can you guys tell me what is the count going to be for the total sample space for this one? What is the total count going to be for the sample space for this one? Man, I was like sitting here looking at these counting problems, man. It's been so long. Calvin's going, or Calvin, you already got the answer? Calvin's going with 24, you think. Okay, thank you for typing that out. We'll wait, see if anyone else types out 24. Just let me know. Whatever you guys get as your answer, just type it out. You don't have to prove it yet. Let's just see what you guys think. Calvin's going with 24? Maybe. I don't actually know the answer. It's a lie, I do know the answer. Could it be that? I don't know. I don't know. So I'm wrong. Well, I don't know, Calvin. Did you write down all the possibilities? Because that is one of the things that it's asking from you, that you write down all the possibilities. And you can just use code letters just like that. AMD for agree, male, Democrat. AMR, MO. And you could do it for disagree. It could be D. Oh, we already used D for Democrat. How about DA for disagree? Maybe you could use that as a code. So DA, that way you don't confuse it with D for Democrat. So you could put DA for disagree, right? I wrote down 1/3 and guess the pattern. I like that, Calvin. I like that. That's not a bad thing to do in math when you can see patterns going in there. Especially when you start dealing with really large possible outcomes. It's easier to do that than write it all out. But there is a pattern. You got 6, Demaya, but we got 6 for the previous one. We got agree male, agree female, right? And that was only 6 right there. Don't forget to take into account Democrat, Republican for each of those ones. The Carwin's going with 18? Question mark? 18? Did you write them all down, Carwin? If you wrote them all down, it could be the right answer. So let's go on to the next one. Let's see here. So I have agree male Democrat, agree male Republican, agree male and no opinion. I'm sorry, agree male and other for their Democratic Party, right? What other possibilities are there for agree? You could also have agree female Democrat, agreed female Republican, and agreed female other for their party. Yeah. So we got the agreed part, right? And for this line right here, we're changing the Democrat, Republican, and other. And then over here, we're changing the males to females. So that's the first ones right there. Next one up is the next option. So I think I've covered agree all the way across the board. I've covered all the people who could agree. They could either agree be male, agree be female, and do Democrat or Republican and other. Now we got to do disagree. So I'm going to write DA for disagree. Male, Democrat, disagree, male, Republican. Oh, Carwin, you're changing your answer to 12. Let's see. Disagree, male, and other. Oh man, this looks so messy. You guys okay with this notation? This looks so sloppy. I hate this, but I got too lazy to write it all out. Never mind, 18. I forgot the no opinion. Yeah, you're going back and forth. That's okay. That's okay. Disagree, female Republican. Disagree, female. Whoops, I switched them. Let's put Democrat first, and then Republican, and then other. Right, so I got those right there. I have all the possibilities for the agree on this first line. I have all the possibilities for the disagree on the second line. And some of you guys are already going in there. Grace is going 18. Calvin, it's 18. No cap. Giselle's going with 18 as well. Good. You guys are counting it out, right? There's 6 possible outcomes for agree. There's 6 possible outcomes for disagree. And there's going to be 6 possible outcomes for the no opinion, right? No opinion. I'm going to go with N. No opinion, male Democrat. No opinion, male Republican. No opinion, male other. No opinion. That M looks like an N. Female Democrat. No opinion, female Republican. And no opinion, female O. Oh, goodness. I did 6 times 4 instead of 6 times 3. That's why I got 24. Yeah, there is a pattern. Right? 6 responses for each of them. Yeah, that looks about right. I don't know about you, but man, that looks god awful, right? But that is a count for all of them. By the way. You can actually see it. Some of you guys might have learned how to count these things using this thing called a decision tree. I don't think it's called a decision tree, a probability tree. I think that's the right word. Have you guys heard of a probability tree? Does that sound familiar at all? Or a tree. I think I'm just thinking of the word tree. I don't know what the actual term is, which I should know. But have you guys ever seen this before? If you're dealing with these topics, right, you can actually have them branch out as a tree. So I'm going to put this to the side. So we were dealing with 3 options here, right? We were dealing with agree, right? Disagree, no opinion, right? So what you can do is actually branch these out. So this is where we're starting off, right? And you could branch this out. They can either agree with it, they can disagree with it, they can have no opinion on it, right? And from there, right? I don't know if this looks familiar or not for you guys, but from there, right, you could branch it out some more. Oh, let me go back. Okay. I'll show this one in a second. Like that. There we go. So get that down real quick, and then I want to show you this tree branching example in a second. Let me know when you got it. Done? Thanks. Sweet. So let's go back over here. So let me show you what I mean. So from this decision, right, you have 3 options you could pick. Agree, disagree, no opinion. After that, you have two options you can pick, male or female. So from the agree point, you can then branch off to either male or female, and you can do that for the don't agree as well. So if you take a look and you just stop right here, you can see there's 6 possible outcomes. Agree male, agree female, disagree female, no opinion male, no opinion female. That's how we got this first part. We got the answer of 6. And if you draw it out as a tree branch, you can actually see the 6 options right there. You can work your way through it and actually get it out. And that's why some people like these branches. And you can go even further now, because the third option was their political party. They were either Democrat, Republican, or other. So from male, you can branch out 3 more times, 1, 2, and 3, making them Democrat, Republican, or other. And you can do that for the females as well, 1, 2, and 3, Democrat, Republican, or other. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So D, R, O, D, R, O, D, R, O, D, R, O. And when you count this out, if you've done this neatly, unlike me, where I did this like a slob, you can actually count it out. There are 18 possible outcomes right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possible outcome. That's why we have statisticians to do the work for us instead. No, you're going to become those statisticians. You don't actually have to draw this out, by the way. There's programs that when you enter it in, they actually draw it out for you. But the idea is you can actually see it. Yeah, and your calculators can do this too. It's just nice to visually, sometimes it's nice to see the branching of it so you can see, right, how those things are connected. You can see how these things are done and how these things are made, right? But you don't have to do this. I'm not making you draw this tree branch or this tree diagram out, but it does help when you calculate probabilities. And I just wanted to, have you guys seen this before, right? I'm hoping you guys have seen this before in your lifetime. Like you've seen this branch before of possible outcomes of things. And if not, you know, hopefully like this is something you can see that makes a little bit more sense as to why it is, right? All I'm doing is just, I'm showing like, you know, I'm just writing out all the possibilities here, but I'm visually writing it out so you can see, oh, AMD, that's agree male Democrat. And that just follows this branch right here. Yeah, I think sophomore year. Okay, good. So you were kind of exposed to it. That's good. And Calvin, I don't know if you saw the next part of the notes already, but you were trying to come up with this pattern, right? Of like it's 6 times 3 or 6 times 4 and all that stuff. And that actually is a pattern that deals with counting. I don't know if you see this or not, but take a look here. For this one, for tossing a coin, there's 2 possible outcomes for that one. And for rolling a 6-sided die, there are 6 possible outcomes there. And if you look at the answer for the sample space, what was the answer? The answer was 12, wasn't it? 2 times 6. You see that? Whereas this one was 6 because there were, get this, 3 outcomes here, 2 outcomes for the gender, that came out as 6. Now we go a little bit further. This one has the ones from the before, which was 6 possible outcomes, but they're adding 3 more. And that's going to be 6 times 3, which gives us the total possibility of 18. So you actually can count this without listing out all 18 possibilities. And that's what leads up into this one right here. This is called the fundamental counting principle. I'm just giving you this heads up right now. Have you ever learned anything and they use the word fundamental? That means it's a big deal. It's like the basis of this principle is done with this theory right here, okay? If one event can occur in m ways, right? Whatever that m is, just a number, right? 2 ways, 6 ways. And a second event can occur in n ways, and that's another number. It could be the same number. It could be a different number. It's just another number for the other event. The number of ways the 2 events can occur in sequence, meaning one happens, then the next happens, you simply multiply the numbers together. And to add on top of this, this can be extended for any number of events occurring in sequence. So if there's 3 possibilities for this first option, and there's 2 possibilities for the second option, And then there's 3 possibilities for the third option, right? That's what happened up here, by the way, right? You have 3 possibilities you can pick from. You can either agree, disagree, or have no opinion. Then there's 2 possibilities for either being male or female. And then there's 3 possibilities for them being a Democrat, a Republican, or other. What I'm saying is, once you count how many possibilities there are for each of these ones in sequence, one, then the next, and the next, you can just multiply these numbers together. When you multiply these numbers together, it gives you the sample space. It gives you the number that's in the sample. It doesn't give you the value of it, but it gives you the total that's in there. So 3 times 2 is 6. 6 times 3 is 18. And you could get that number without having to list this all out. And I think that's really neat, that you can actually calculate how many possible combinations there are for things. And yeah, I think that's super neat. Like, check this out, for example. Do you guys have that, by the way, in your notes, or does it already, do you have to type it? Is this already in there in your notes? I forgot to check. So that way I can go to the side. Can I go to the side, or are you guys still, you have to fill in the blank? All right, let me leave that open for you guys so you can fill in the blank before I show you this other example on the side. It's just really neat to look at. Like this rule, this fundamental counting principle is just such a cool thing to do. I think it's a cool thing. I'm kind of nerdy, but check this out. Like, you know, the sample space for, you can keep writing, but you know the sample space for flipping a coin, right, is heads or tails. So the sample space is 2. Now, if you want to flip a coin twice, how many possible outcomes are there for you flipping a coin twice? It's no longer 2. It becomes 4. That's right, Calvin. That's right, Lewis. That's right. And you can list it out. It's either heads, 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 tails, tails, heads, tails, tails, right? 4 possibilities, right? 4 possibilities if you're flipping a coin twice in sequence. Now, if you flip it again on the 3rd time, it's no longer 4 possibilities. You guys got the next number? What if you flip the coin 3 times? How many combinations are there if you flip a coin 3 times? It's not 6. It's not 6. It is 8. It is 8. That's where things start to get weird, but it kind of makes sense. There's 8 possibilities if you flip a coin 3 times. You ready for this? You ready for this? You ready for this? Here's my branch. You don't have to draw this. You don't have to put this in your notes. I just like checking this out, right? So let's say you flip a coin. I can spell flip. Jeez, knock me. What are you doing? So let's say you flip a coin, right? And this is where we start. First option, you're either going to get heads or you're going to get tails, right? So the first one is 2. If you do it again, you can either get heads again or you can get tails. And if you got tails first, you can get heads again or you can get tails, right? So that's 4. Then do it again. Heads, tails, heads, tails, heads, tails, heads, tails. And now you'll say, knock me, that's such a headache to look at. But look, count it out. 1, 2, 3, 4, 5, 6, 7, 8. And if you don't like looking at it like this, you can actually write them out. You ready for this? If you go along the branch up here along the top side, if you're flipping a coin 3 times, you could get all heads. That's one of the possible outcomes. The other possibility is heads, tails, heads, right? Heads. Wait, why did I do that one first? I'm going in order. Heads, heads, tails is the other possibility. Then you can go this way. You can get heads, tails, heads, or heads, tails, tails. And that covers up everything up here for this part. Then you can go down here. This will be tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Those are the 8 possibilities, in total. And yes, Calvin, that is right. That is the power rule pretty much being applied if it is the same number, because you're just multiplying, right? And since I'm multiplying by the same number by flipping the coin repeatedly, the next one after this is going to be 16, right? If I flip the coin the 4th time, there's 16 possibilities that you can list out for that one as well. And you'll say, but isn't heads, heads, tails the same thing as heads, tails, heads? If you're measuring for probability and you're looking to see like, oh, I want to get at least 2 heads, then yeah, those are the same. But they are in the sample space and they are unique from each other. Getting heads, heads, tails is unique from getting heads, tails, heads. That's just something to keep in mind when you're listing that out. Anyways, hopefully you guys have finished copying this down. If not, let me put this back on the screen for you, for those of you who are filling in the blanks for your notes, right? If one event can occur in m ways and the second event can occur in n ways, and then those m and m don't have to be the same numbers. They could be different numbers, but they could also be the same. And the 2 events occur in sequence, you can just multiply the number of ways together and get the total number in your sample space. I really, really like this one. It's just so much easier than having to draw it all out. Now, flipping a coin, I don't know if you saw, if you just do it 3 times, there's already 8 branches, and it gets a little annoying. You do it 4 times in a row, it turns into 16 branches. And if you do it 5 times in a row, it turns into 32 branches. And I don't know if you noticed or not, I was already struggling to draw 8 branches. Could you imagine how bad I would have to, how much trouble I would be in to draw 32 branches? Yeah, I'm just not going to do that. But yeah, hopefully you get the idea. So what was nice about the fundamental counting principle is it helps you count the total possibilities of ways without having to list it, right? Without having to list it. Anyways, hopefully that makes sense to you guys on that one. Let's do another one. Let's do an actual problem here without having to list it all out. Okay, let's do this problem right here. You're purchasing a new car. The possible manufacturers, car size, and colors are listed. So there's 3 things that you're going to be taking into account, but that's not what we're multiplying by. So we're going to look at each of these places here. So the first thing up that you're going to be looking at is the manufacturer. Right? How many manufacturers are you picking from in this particular example? 1, 2, 3. So there's 3 possible choices for your manufacturers. Only one of which I would pick because I'm Asian. I don't even think GM is still around. Do you guys know if GM is still a company that's still making cars? I know Ford is still around. I know Honda is. I don't know about GM. Is General Motors still around? Anyways, that's not important. Next one up, right? Next thing you need to look at is the car size. Move this over here. There we go. So, all right, next one up is the car size. What car size am I looking to buy? It's the owner of Chevy and Cadillac and Buick and GMC. Oh, okay. So they okay, I got you. They own all American cars? I guess, okay, they own Chevy, but so that means they don't own Ford, right? OnStar. Okay. So they're still around. Yeah, they're still around. All right, then. Ford is its own. Okay. How about Dodge? Dodge is his own too, right? Dodge is also American. Ford owns Lincoln. Yeah, so Lincoln is part of Ford. Dodge is owned by Chrysler, I'm assuming is what you typed out. Chrysler? Man. So many different car brands. Anyways, we're just to keep it simple for our sake, we're only looking at these 3. Ford, GM, and Honda. Next thing up, right? Toyota Lexus. That's very Asian, and that is also the car that I drive is a Toyota. Yeah, very reliable. Yeah, I still have my car from college, from 2007. My car is 13 years old. Anyways. Next thing up, looking at the car size. How many car sizes are we looking at for this example? We're looking at a compact and we're looking at a mid-size. So that's 2 different car sizes, right? 2 different car sizes. Last thing up is going to be the color, right? The color. How many options do we have for our color here? White, red, black, or green. 4 possibilities, right? 4 possibilities. So using the fundamental counting principle, how many possible combinations of cars can you be purchasing if they follow under these 3 categories? All you got to do is multiply them together. 3 times 2 times 4, and Calvin's already typed it out there. That's going to equal to 24 possible combinations. 24 possible combinations. And if you don't believe me, you can actually do a tree diagram to draw it out, or we could just write them out as well. You ready for this? You can get a Ford. I'm going to be lazy. Okay? You can get a Ford, right? That's compact, right? And white. You can also get a Ford that is mid-size and no, I did this wrong way. I got to list out all the possible colors. You ready? Ford, compact, and instead of white, you can get it in red instead. And then you can do it again. You can get a Ford, compact, and you can get that in black with the color. And then you do it one last time. You get a Ford. Jeez, I don't actually want to do this, but you guys can. Compact, and the last color is green. See that? They should give us iPads with pens to take notes like this. Yeah, it would be nice. Instead of iPads, though, you don't need the iPad. iPads are ridiculously overpriced. I mean, they're nice if you are looking to do something for personal stuff, but if you're just doing to take notes, I really wish they had, instead of giving you the Chromebooks that they gave you a touchscreen Chromebook where you can use a pen or a stylus to write on it, because that would have made more sense if we're going digital and they want you to use more of these electronic things. They should have gave you a touchscreen Chromebook, which is only like $100 more, but you know, it's $100 more and money. But you know what's actually going to happen is you guys are going to graduate, move on, and then things are going to get cheaper. So then future kids will have that technology. So, you know, you could be happy for those kids knowing that they got better stuff than what you guys got. All right. Anyways, I'm not going to list out all of these, but like I said, you could do a tree diagram. You could list them out like this. They all work the same way. With the tree diagram, it might be a little bit easier, right? You could do it vertically as well, right? You can say that you have a Ford right here, and in the middle you have General Motors, and then over here you have a Honda, right? So that's the 3 possibilities there, right? And then the car size for each one of them, right? For a Ford, you could be going with the mid. Is it mid or is it compact? Oh, it's both. Okay, so you can go with compact or mid, and you can do that for all of these, compact or mid-size, compact or mid-size. And right now we're at 6 possible outcomes. And then after compact or mid-size, you can list out all the colors: white, red, black, and green. So for this one, you can have 4 possible outcomes: white, red, black, or green. 4 possible outcomes for this one: white, red, black, or green. 1, 2, 3, 4. White, red, black, or green. Oh, you know what? I'm an idiot. Why am I doing this by hand when I could just do this? Copy, paste. Work smarter, not harder. Boom, there you go. Are you telling me, Nakmi, that you had this technology for a while and you forgot that you could copy and paste? Yes, Nakmi, I forgot. Get off my case. I'm tired. All right. Whoops. There you go. So that is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And there you go. 24 possible outcomes for the different colors, for the different makes, and the different sizes of this one right here. But again, this is one possible way of doing it. The other one is if you just use the fundamental counting principle and you just multiply them together and get your answer of 24. I think that's a little bit easier. I think it's a little bit easier, honestly. Honestly. All right. So can you guys do this? But for this one instead, your choices now include a Toyota for your make. It also includes a large car, and it includes two more colors, tan or gray. Can you calculate how many different ways you can select one manufacturer, one car size, and one color? Don't do a tree diagram for me on this one. Just tell me what would the answer be for this one if you were looking at this same example, but you're going to add in here a Toyota, right? So I'm going to add in here a Toyota, right? The other thing you're going to add in here is the large car size and the two more colors. You're going to add in the colors tan and gray. So can you guys do that real quick for the U-Try? It's the same one as up here, except you're going to add in a new car model, which is the Toyota. The car size, compact, mid-size, and then also add in large. And then add in the two more colors of tan and gray, and see what you guys get as your possible count for that right there. Can you guys do that real quick? Don't type it out into the chat just yet. Give everybody a chance to calculate that one out for the U-Try for that one. Let's see what you guys get. Random side note, do you guys spell gray G-R-A-Y or G-R-E-Y? G-R-A-Y? G-R-E-Y with an A? You ever wonder why they have two of those spellings? Oh, it's just, more people typing out with the E. Question is it gray or is it gray? While you guys are calculating this, I'm going to go ahead and Google that because it's going to bother me. I feel like I've looked this up before. Gray or gray? First thing that comes up before I finish typing it out. It confuses me sometimes. I think it depends. Calvin. Gray? Gray? Gray or gray? It depends on where you live. Huh. What is this? Are you trying to advertise to me? Get out of here. Gray usually refers to the color. It can be used in an adjective when we want to say that the color of something is a shade of gray. So it's used as a verb for when something turns gray. This is a long article. Do you have like a too long, didn't read type of thing? No, I don't want to read all this. I'm curious, but I looked it up and it says people can use either. Oh, okay. Yeah, that's what that one was saying. So it all depends on where you're from was the other part of it that I was trying to read in there, like which part uses E and which part uses A. But as long as they're both acceptable. Demaya, you're just typing orange just for the sake of typing an orange? Yes. All right. I'm assuming that's the knock me, move on type of notes. All right, let's go on here. So what's the answer for this one, guys? So if you add in the Toyota, there's no longer 3 manufacturers, right? If you add in the Toyota, there are now 4 manufacturers, right? If you add in another size, there are now 3 different sizes that you're going to go into. And if you add in 2 more colors, there's going to be 6 colors in total. And Michael's typing in that he got 72. And I'm going to go ahead and trust you on that 4 times 3 is 12. 12 times 6, I'm going to trust you, is 72. And I agree. 72 possible combinations. Meaning if you were to draw this out, the tree branch would have 72 different branches by the end of it. And notice how this one doesn't say to check your answer with the tree diagram, right? We're just going to be happy with that and leave that there. All right. All right, that's enough of that one. Let's go on to here. I think this will be the last example for today before I let you go. So let's take a look here. The access code for a car's security system consists of 4 digits. Each digit can be any number from 0 through 9. which by the way is like your PIN number, right? For those of you guys who have a bank account or have seen someone with a bank account, you guys understand that there are PIN numbers that are included with that, which is a 4-digit number as well. Yeah, so looking at this right here, let's say we wanted to count how many possible combinations are there if you're looking at a digit from 0 to 9 are possible for this security system. Okay, let's say I was looking at this and each digit can be used only once and not repeated. So let's say I was trying to find this access code. And one of the rules is that I can only use the number one time and I cannot have it show up again. Meaning a code like 3513 is invalid, right? Because the 3 shows up twice, right? 4444 is another one that is invalid because the 4 is repeating itself, right? So whatever your security code is, 5137, that one would work out because the number only shows up once and it's not repeated. How many combinations would there be for that said code? How many combinations would there be for that said code? Now, when you attack these types of problems, the best way to attack it is to count how many possibilities there are for each of these ones. I don't know if you guys saw this or not, but what helped me to do this problem earlier, right, was to see that there were 3 types of cars and then multiply it with the 2 types of sizes and multiply that with the 4 types of colors. Now you'll say over here, there's no car sizes, there's no colors, there's no nothing of that nature. There are only numbers from 1 to 9. It's not actually 81, Calvin. You're going to be surprised by the answer for this one, by the way. How many possibilities are there for the first digit? How many possible numbers can you pick from for the first digit? Not 40. How many possible numbers can you pick for the first digit if each digit can be any number from 0 to 9? 10. Giselle, that's right. Remember, we did this in the last chapter. We counted out from 0. So 0 is the first number. So that's 1 right there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 0 to 9, there's 10 numbers. So for the first digit, there's 10 possibilities, right? I'm not saying the first digit is the number 10. I hope you guys understand that. That's the most common mistake that people make. That first digit has 10 possible choices that you can pick from, right? 10 possible choices that you can pick from. Careful, Calvin, we're not done yet. We still need to pick the second digit, the third digit, and the fourth digit. So we're moving on now. How many options do we have for the second digit? Yeah. We're doing 4 digits. So we got to do it for all 4. Because this security system requires 4 digits. So how many options do we have for the second digit? How many options do we have for the second digit? Do you guys have any ideas? The first digit, we had 10 options. We had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We had 10 options for the first one. Michael is saying that the second digit only has 9 options. Only has 9 options. And Michael, you are correct. There's only 9 options left for the second digit. Why is that? Why is it not 10 as well? Why are we not picking 0 through 9? And Calvin's saying it right there. And so is Michael, you cannot repeat it. So whatever you picked for that first one, that number is no longer going to be used. So like Calvin said, what if you picked 1? Then the second digit can't have a 1 there. So you're going to count 0. Can't count the 1 anymore. So it's 0, 2, 3, 4, 5, 6, 7, 8, 9. There's only 9 digits left to pick for the second one because you can't repeat it, right? And if you follow that pattern, right? If you follow that pattern, that's what I'm saying. Let's say, for example, then I have my 4-digit code is going to be the first number was the number 1. If you pick the number 1 for the first digit, you can't pick the number 1 for the second digit anymore. So then the second digit needs to be a different number, like let's say 5. So since I can't pick, right, for this one, you can't pick 1 anymore because it was picked on the first one, right, since it was already taken. There's only 9 options for this one now. There's only 9 possible outcomes for it. Right? Does that make sense? Since you can't repeat it, it loses one of the numbers there. And you can keep going with this. Once you take a number and you put in the first one and you take another and you put in the second one, the third digit now, you guys figure it out, only has 8 options now. And the fourth digit will only have 7 options. You guys okay? So how many possible combinations can you have for your code? You ready? How many possible combinations can you have for your code from 0 to 9? You're going to get 10 possibilities for the first digit times 9 possibilities for the second, 8 for the third, and 7 for the fourth. I can't do that in my head. I'm going to multiply this out with my calculator, which is going to be 10 times 9 times 8 times 7. And that's going to give me 5,040 possible combinations if you don't repeat your number. There's 5,040 ways to write a 4-digit number without any of the numbers repeating. Without any of the numbers repeating. That means if you were to sit there and list them all out, like we did with the heads and the 6-sided die, right? You'd list out 5,000 different ones. And you ready for this? The first one up would be 0, 1, 2, 3. Next one after that would be 0, 1, 2, 4. 0, 1, 2, 5. 0, 1, 2, 6. 0, 1, 2, 7. 0, 1, 2, 8. 0, 1, 2, 9. 0, 1, 3, 2. I can't do 30 because the 0 will repeat, and I can't do 31 because the 1 would repeat. So I have a better chance of guessing your PIN than being injured by a toilet. We'll talk about those odds next time, Calvin. But yeah, the chance of you guessing a PIN would be, if the numbers couldn't repeat, would be 1 out of 5,040. But yeah, 1 out of 10,000. Yeah, I mean, if that's the true statistic of that. So you guys understand what this represents? It's the count. If I were to count all the possible combinations of PIN numbers where the numbers can't repeat themselves, there's 5,040 of them, right? There's 5,040 of them. So hopefully you guys can see that and you guys understand that. And I'm not going to sit here and list out all 5,040 of them, but that's just how that is. Okay. Anyways, there's a couple more examples. We're going to talk about them. Actually, you know what? Let's do this one real quick. Number 2, I'm going to do this one for you just so you can write this down. Each digit can be repeated, meaning that you can repeat the numbers. So that means that the first digit has 10 options. The second digit, if you can repeat it, is also going to have 10 options. The third digit is also going to have 10 options. And the fourth digit is also going to have 10 options if you're allowed to repeat the digits. Meaning, if you're allowed to repeat the digits for your PIN code, there's going to be 10 times 10 times 10 times 10 possible ways to make your PIN. And your PIN would be one of 10,000 possible combinations for this one right here. 10,000 possible combinations just from 4 digits. Just from 4 digits, right? There's 10,000 possible combinations from 4 digits. So if you're trying to sit there and crack someone's PIN code and you don't know it, you could try all 10,000 numbers before you find the right one, if you really wanted to. Because most people's PINs do have numbers that repeat. Sometimes they repeat more than once, but it's not any more safe or less safe than something that doesn't repeat if you don't tell them that it repeats. Anyways, guys, I'm going to stop it there, right? We're going to continue with this. I'm hoping that it makes sense. I'm hoping that you guys can see that counting different ways is a little, like, it sounds a little boring, but I think it's kind of neat, honestly. Like, you can actually count how many different possibilities there are. And if you have that skill down, just like Calvin was already doing, you can actually calculate the chances of something occurring if you can count all the possibilities. And apparently, chance of being hit by a toilet is 1 out of 10,000. And man, that sounds kind of crazy. But we'll talk about that in the future of how to calculate those probabilities, okay? So right now we're just talking about the countings. No homework yet. We're going to go ahead and continue these notes on Thursday, all right? I'm going to call it there, guys. Have a good rest of your day. I'll see you guys on Thursday. I do have office hours later today if you need to stop by to ask any questions about anything, okay? Other than that, guys, have a good rest of your day. I'll see you guys later. All right? So long.